In this video, I'm going to really dig into how to balance equations. And so I'm going to start that even before balancing. I'm just going to start with feeling comfortable reading chemical equations, which if you don't feel comfortable doing that, you can't balance equations successfully. And so if you want to skip around to the video, I've put the 3 parts of this video up on the front. So part 1 is just understanding how to read chemical equations. Part 2, I'm going to go over the 4 don'ts of balancing and basically explain what the steps are to actually balancing equations in general. And then in part 3, I'm just going to do practice problems, kind of drill those skills. So, all right, part 1. Just understanding how to read chemical equations. So we see this here, and the most important thing that we can do is to separate it into 2 overall parts. And those parts are always separated by the arrow we have right here. So our arrow here is the reaction arrow, and all it says is that a change happened. We had something and now it's not that exact same thing. And what it doesn't say is how long it took. And so, for instance, this example is actually the process of iron rusting, which, as you know, doesn't take, a second. A lot of students kind of think, okay, I see the reaction arrow. That means that something caught on fire or exploded and it took a couple of seconds and then you have new chemicals. But chemical changes can happen over the span of days, months, years, millennia. So never look at this arrow and think, I know how long that took. And so now that we have our separation, we have basically our before and our after. And so in chemistry, we call that the reactants or reagents and the products. And so these literally just do mean before and after. The reactants or the reagents, same thing. They're just what you had before your change. And your products are what's there after the change. All right, so in its broadest strokes, this is what we care about with a chemical equation. And so now I want to kind of dig into the numbers because there's these 2 different types of numbers, and it's really important for balancing and everything else that you understand the difference between them. So first we have kind of our regular sized numbers that always go to the left of our atom or molecules, and this is called the coefficients. And what the coefficients mean is how many of each molecule you have in your reaction. So in this reaction, it means that we have 4 atoms of iron, we have 3 molecules of O2, and when we have that combination and then we have our change, we make 2 molecules of iron oxide or Fe2O3 or rust. All right, so that's the coefficients. It tells us how many of each molecule we have in this reaction. And the other number is always to the bottom right, and it's called a subscript. And this tells us how many of each atom we have in that particular molecule. So that means we can see that our O2 molecule consists of 2 oxygen atoms, and our iron oxide molecule, every single one has to have 2 irons and 3 oxygens. And so if there's no subscript, for instance, over here on our original iron atom, if nothing is written, it means it's an implied 1. Every single iron atom, there's just 1 of them, and we need 4 individual iron atoms to go ahead and combine with oxygen. So if you don't see any subscript for an atom, it just means, hey, that only takes 1 of them. So there still is a subscript there, it's just invisible. All right, so now that we kind of understand how to read chemical equations, let's go ahead and just do some pre-balancing practice problems to make sure we really understand how many of each element we have in our molecules, because understanding that is super important for balancing. Okay, so here we have a problem that's fully balanced, and let's go ahead and just break down how many of each element we actually have. All right, so first let's deal with our coefficients. So right here, our coefficient of 2, that means we have 2 C2H6 molecules. And then over here on our 7O2, this means that we have 7 molecules of O2. And now on the product side, it means that we have 4 molecules of carbon dioxide, and it means we have 6 molecules of H2O. All right, and because this is balancing, we're always going to have this separation between the products and the reactants, because we really want to see, is it balanced? Do we have the same amount of every single type of element on the left-hand side as we do on the right-hand side? So our elements are carbon, hydrogen, and oxygen. It will always be the same exact elements on the left-hand side and the right-hand side. You'll never add or remove elements from left to right. And so now let's go ahead and add up exactly how many we have of each. So for carbon on the left-hand side, we can see that we have 2 here, 2 here, 2 plus 2 is 4. We have 4 carbons. Another way to do this is to multiply the coefficient by the subscript. So up here, we could multiply 2 times 2 to also get us to 4. And so now for hydrogen, again, we have our two options. Option 1, if you draw it out like this, we could say, okay, 6 plus 6, that equals 12. I have 12 hydrogens. Or you can go ahead and say 2 times 6, multiply coefficient by subscript, that gets us to 12 as well. And so same thing goes for oxygen. So we can count up all of our oxygens right here, 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2, or we can do 7 times 2 and get to 14. And so now let's make sure it's balanced. We want to make sure we have the same on the left-hand side as we do on the right-hand side. So here we have our first invisible one. This carbon has nothing written there, which just means it has a subscript of 1. So we can either add up our 1, 2, 3, 4 carbons, or we can do 4 times 1 subscript times coefficient to get to 4. And now for hydrogen, we can do 2 times 6, or we can add up all of our hydrogens right here. Either way, we get to 12. And now for oxygen, we can see that we have a little bit of a split, right? So we have O2 here in our carbon dioxide molecule, and we also just have a single O right here in our H2O molecule. And so for balancing, we never need to care, oh, how many came from one, how many came from the other, and indicate that. All we ever care about is how many oxygen atoms are there overall on this right-hand side. So we're just going to add up both of them. So for the carbon dioxide, we can do 4 times 2, or we can add up all of our 2's right here. So that gets to 8. And then over here on our H2O molecule, we have again this invisible 1 subscript. So 6 times 1, or adding up these 6 right here, that gets us to 6. So we have 8 plus 6. We don't really care. Again, you don't have to show this work. It just matters that this total is correct. So we have 14 oxygens total. And now we can see that's really balanced, right? We have overall 4 carbons, 12 H's, and 14 O's. All right, so now I want to do this one more time just to make sure you really understand how to read those chemical equations. And so we're going to do just one molecule. So this has a coefficient of 2, and it's aluminum sulfate. So let's go ahead and break down exactly what to do. In this molecule, we have aluminum, sulfur, and oxygen. And we also have something new that we didn't have in our first equation. We have this parentheses, right? So when we have a parentheses like this, and then a subscript, it's saying, hey, this 3 applies to everything inside that parentheses. So what it's really trying to say is, hey, we have this kind of unit, this chunk called SO4, and we have 3 chunks of SO4. So when you look at this, what you should see is this, that for every single molecule of aluminum sulfate, we have 3 chunks of SO4. And so that means that when we're multiplying our coefficient and our subscripts, we have to also include any subscript that happens outside of parentheses. So when I'm multiplying out, for aluminum, it's just regular. I do 2 times 2, coefficient times subscript. I have 4 aluminums. And now when I do sulfur, I have to consider, first of all, this sulfur has an invisible 1 right here. And so when I'm multiplying, I do 2 times this invisible 1. And then I also have to include this 3, because this 3 is outside the parentheses, so it really does apply to everything inside the parentheses. So overall, my equation for sulfur will look like this, 2 times 1 times 3. Every single coefficient that applies, and every single subscript that applies. So when I do this, I get 6. So I have 6 sulfurs in this molecule that's balanced with a 2. And the other way I could have done that is to say, okay, well, looking over here, each molecule of this includes 3 S's, right? 1, 2, 3. And so if I had 2 of those molecules, it makes sense that I would have a total of 6. All right, and so last we have oxygen. We have our 2 coefficient, so that's going to have to get multiplied by every applicable subscript. So in this case, we have 2, and it's going to be having to times by this 4, so 2 times 4. And then because oxygen is also in this parentheses, 3 is also applicable. So we're going to have to multiply it by 3 as well. So 2 times 4 times 3 is 24. So we have 24 oxygens. The other way to do this is, again, to look back and kind of look at our expanded SO4 groups and say, okay, in each expanded one, I had 4 plus 4 plus 4, I had 12 already, and then because I had this coefficient of 2, I had 2 molecules of that, so it's really 12 plus 12. That's another way to get to 24. All right, so that's our intro to reading equations, and now that we have this, we can go ahead and start to learn how to balance. All right, so here we have an equation. H2 plus O2 turns into water, and so let's go ahead and just check how many elements of each we have on both sides. That's the first step to any balancing equation. So we always draw a little line here to separate the reactants from the products. We line up our elements. In this case, we have hydrogen and oxygen. They're always going to be the same on both sides. I like to make sure that I'm always completely lined up, so my H is right next to my H, my O is right next to my O. And now we just count. So in this case, there are no coefficients. So we just have 2 H's and we have 2 oxygens. And then on the right-hand side, again, no coefficients. We just have subscripts. So we have 2 H's and then nothing is written for oxygen, which of course means it's that implied 1. So, all right, this we would call an unbalanced reaction, which means we don't have the exact same amount of each element on both sides. So even though hydrogen is balanced, we have 2 on the left and 2 on the right, and even though the fact that oxygen is only off by 1, and there's 2 on the left, 1 on the right, this is still unbalanced. It's not completely the exact same for every single element. Only if we had the exact same for every element is it balanced. Until then, it's unbalanced. So now I'm going to go ahead and redraw this exact problem, but I'm going to go ahead and balance it. So first, let's just catch up to our equation up top. All right, and so now we're ready to start balancing. And so to balance, we change the coefficients. And so we can't really make anything less than what it starts out with. This is just how we start our problem, and we can't decrease the number of anything. All we can do is add to it. So what I'm going to do is I really want to make this number of oxygens equal, right? And so the way I'm going to do that is by adding a 2 here. And so as soon as I add any coefficient, I immediately cancel out any element that was affected by that. So I put a coefficient in front of this water, and that affected both hydrogen and oxygen. So now this is inaccurate and this is inaccurate because they're going to be something else. So now multiplying, I do 2 times 2, that's going to be 4 hydrogens, and I have my implied 1 here, and so I do 2 times 1, that's now 2 oxygens. All right, so now I have the reverse problem. My oxygens are balanced, but my hydrogens are not. So I go to my left-hand side and I say, okay, how can I balance that? And so what I have to do is go ahead and add a 2 coefficient right here, because now 2 times 2, this hydrogen is 4. And because that coefficient was only talking about H2 and we had this plus sign right here, this O2 was unaffected by that coefficient. So this O2 remains as just the 2 right here. We don't change that at all. And so now this is balanced. We have the same number of every element on both sides. And so we're allowed to either leave it like this, where there's nothing right here in the coefficient for O2, or you can go ahead and draw in a 1, because again, in a lot of chemistry things, if there's no number written, it just means an implied 1. All right, so now let's go ahead and learn some things that we definitely can't do in these problems. So don't, number 1, don't change your subscripts. So again, let's rewrite how this problem begins. So for students starting out balancing, it can be really tempting to go, oh, okay, I need to make this even. So what I'm going to do is I'm just going to add a 2 right here. And then look at me. Look, I went ahead and I have 2 oxygens on the right-hand side, and now I'm balanced. So we are not allowed to do this. And we can only ever change the coefficients in balancing, never the subscripts. And this because the subscripts are trying to really tell you information about that molecule. This is saying, hey, we have hydrogen and oxygen and we're making water. If you add that 2 here, now it's saying hydrogen peroxide. That's not water. This completely changes our reaction. So we're definitely never allowed to ever change subscripts. Those subscripts are locked in 100%. All right, don't number 2. Again, catching the problem up, don't add coefficients in the middle of molecules. So if we want to say, oh, okay, I'm just going to increase the number of oxygens on the right-hand side, I'm going to add a 2 right here. And now I don't have 1, I have 2. We are not allowed to do this. You can't add coefficients in the middle of the molecules to avoid some elements. You can only add them on the very left-hand side, and they have to affect the entire molecule. So if you want to put that 2 there, you have to put it here, and it's going to affect hydrogen and oxygen. All right, next. Don't give a final answer with fractions or decimal coefficients, only whole numbers. So again, some students say, oh, okay, I'm going to make the number of oxygens on the left-hand side less. I'm going to do this. And then multiplying 1/2 times 2, that's now 1, and now I'm balanced. Can't do that either. We really can't represent half of a molecule. These molecules are set, there are a certain amount of bonds, there are a certain number of atoms they have to be stable and to exist. So we can't just say, I have half an O2 molecule. That doesn't exist in real life, and so it's not going to exist in balancing. We can only give final answers with whole numbers. All right, and so our final don't is don't give non-reduced answers. So let's say that somehow throughout the process of balancing, you ended up with these coefficients. Now going through, this is actually balanced because the h's on the left-hand side would be 4 times 2, 8 on the right-hand side, on the left-hand side, and the O's on the left-hand side would be 2 times 2, so 4. And then on the right-hand side, you'd have 4 times 2, so 8 H's, and then 4 times R1, so 4 oxygens. So this is balanced, so why can't it be your answer? Well, because it's not the most reduced answer. We know the real answer is over here. It's the coefficients 2, 1, and then 2. So those are the lowest whole numbers that create a balanced equation. So if you get 4, 2, 4, all of those can be divided by 2. So when you're doing balancing problems, it's a good thing to, when you're done, go ahead and double check, oh, okay, can I actually divide all of these coefficients by something and get whole numbers? So in this case, we could go ahead and we could divide all of these by 2, in which case we would just get the actual answers that we know are correct. So just a good kind of double check at the end. You don't want to give coefficients that are higher than they need to be. All right, so now that we've gone over how to read chemical equations and all the things we can't do, let's go ahead and do a couple of practice problems. So the only other rule is just kind of a guideline. I think it's good to do whatever element appears in the most molecules you want to balance last. So in this case, we can look at our first problem, and we have carbon, hydrogen, and oxygen. They're only in one molecule each, but in the right-hand side, we have oxygen in both molecules. So oxygen is the element that appears in the most molecules, so that means it's the one we're just going to go ahead and do last. So let's go ahead, we start all of our balancing by just tallying up how many of each element do we start with. All right, so separating the left and right hand side, lining up our elements, and again, see how I have all of my elements completely lined up so I can compare carbon to carbon, hydrogen to hydrogen, oxygen to oxygen. I don't want to have these out of order or else I'm going to start to get confused. All right, and so without coefficients, and then I have 1 carbon from the implied 1 subscript, I have 2 hydrogens, and for oxygens, I have 2 plus 1 at the very beginning. So that gets me to 3 overall oxygens. All right, so again, we're just going to now balance anything besides oxygen. So let's just go ahead and start with carbon. I'm going to balance carbon by putting a 2 here, and then immediately canceling out anything that 2 affects. So that's going to be carbon and oxygen. And now reassessing, I now have 2 times 1, 2 carbons, and for oxygens, I now have 2 times 2, so 4, and then I still have this one over here, so my math looks like this. Now I have a total of 5 oxygens. All right, so next I'm going to go ahead and balance hydrogen, and so I need to make this 2 a 4, so I'm going to do that by putting a 2 right here. So now crossing out what that coefficient affected, it affected hydrogen and oxygen. Both of these are not accurate anymore. So now I have 2 times 2, so that's going to be 4 hydrogens, and I'm going to have for oxygen, I still have my 2 times 2 for right here, so that's still 4 from the carbon dioxide, plus I'm going to have now 2 times this 1. So now I have 6 oxygens. All right, so now all I have to balance is oxygen on the left-hand side. I need to get to a total of 6, so what I'm going to do is go ahead and put a 3 here, cross that out. The only thing it affects is the oxygen, doesn't affect carbon or hydrogen, and so now I have 3 times 2, so that is a total of 6 oxygens. And now I'm completely balanced because each side has the exact same number of each element. And so I can either leave this little spot blank, or I can put a 1 there. Doesn't matter. All right, so now let's do one more example. So first separating it into left and right, lining it up on the left-hand side and the right-hand side so I can easily compare the exact same elements, and filling in how many I have of each element before there are any coefficients. So hydrogen, from this implied 1, I have 1, plus the right-hand side, I have 2, so that's a total of 3 hydrogens. For silicon, I just have the implied 1, for chlorine, 3, and for oxygen, just the implied 1. And again, following our rule up here, in this case, hydrogen actually appears in every single molecule, so we're definitely going to balance that last. And then on the right-hand side, for hydrogen, I have 10 plus 1, so 11. For silicon, I just have 10, chlorine, I just have 1, and oxygen, I have 15. All right, so skipping hydrogen because that appears in all the molecules, we're going to do that last. Let's do silicon. So I have to balance on the left-hand side by making this coefficient 10. And so instantly cross out anything that coefficient affects. So it affects hydrogen, silicon, and chlorine. Now let's go through and balance. So now we have 10 times 1 for hydrogen, so 10, plus the 2 right here. So we have 12 hydrogens. For silicon, we just have the 10 times 1. For chlorine, we have 10 times 3. And oxygen is the same, it just has that 1. So now I have my silicons balanced, so let's go ahead and balance the chlorine. And so I picked this example because I wanted to show you guys that there is no limit to what your coefficients can be. We see we have 30 chlorines on the left-hand side, and so it means that we have to go all the way from just having 1 chlorine on the right-hand side to 30. And there's no way to do that besides just putting a 30 here. So sometimes your problems are going to require you to have pretty big numbers for your coefficients. So now instantly cross out anything that 30 affected. It affected hydrogen and it affected chlorine. And so now redoing everything, for hydrogen, I have the 10 here, plus the 30 here. So I have 40 hydrogens. And for chlorine, I just have the 30 times this 1, so now 30 chlorines. Alright, so now doing oxygen, saving hydrogen for last. The only thing I can do is on the left-hand side increase that 1 into a 15. And so I do that by putting 15 right here. And then crossing out hydrogen and oxygen, both of those were affected. So now for hydrogen, I still have this 10 times 1, so 10. And now I have 15 times 2, so that's 30. So I have 40 total hydrogens. And now for oxygen, I just have this 15 times 1, so 15. All right, so now if I look, I actually have balanced everything. Oxygen is good, chlorine's good, and hydrogen is good, even though I didn't even deal with it. But just by balancing everything else, I happen to balance the hydrogens too. That's another reason we do whatever element appears in the most molecules last, because sometimes we don't have to do it at all. Alright, I hope this intro to balancing helped you. I'd say for these problems, it's really just a matter of getting in there and doing a bunch of practice problems. Also, if some of your problems take you like 20 minutes or a half hour when you're just starting out, don't worry, that's totally normal. You aren't supposed to just get them right away. Just give yourself time and do a bunch of practice problems and you'll get it. Hey, I hope you liked that video. Please feel free to subscribe, click around and watch my other tutorials. And as always, happy studying!